Hello everyone, and welcome back to our R programming journey. Today we're going to be focusing on how to do some basic discrete random variable probability theory in the R programming language. As you already know, if you do know something about discrete probability and random variables, you should know that if we want to solve problems for what's the probability that you have more than 10 customers that come to your restaurant in a particular evening, you can typically just use summations on the associated probability mass function and get the associated answer. So when it comes to implementing discrete probability in R, you just need to know just the fundamental tools on how to sort of implement the associated probability mass function. For example, how to do factorials, combinations, permutations, derangements, doing random numbers or something like that, how to choose particular values that satisfy criteria, doing random samples, for example, doing the expected value variance, second moment of a random variable if you have the PMF, and how to actually do summations for probability mass functions. So let's start off with the basics of the tools that we typically need when we're building probability mass functions. So if you are familiar with, for example, the binomial, the Poisson, the hypergeometric, the multinomial, the negative binomial, and probably other discrete probability mass functions, the factorials are one of the more common calculations that you definitely need to know how to implement. So to do a factorial in R, you can just use the function that is already predefined as factorial. For example, if you just do factorial 5, that's going to calculate 5 factorial, which we know to be equal to 120. And if you do, for example, the factorial of 0, we typically do define this as 1, and R also defines factorial of 0 as 1 as well. Now, one could be a little bit more creative and say, okay, well, can I evaluate factorials of non-integer numbers? By the classical definition of factorial, that would be undefined. But if we type in, for example, factorial of 0.5, it will give us an answer. So if you know a little bit about some special functions, this value of factorial is extended via what we call the gamma function, which is often used in some more important probability density functions such as the chi-square, the t, the gamma distribution, and several other applications of it as well. Right, so this is how we define the factorial in R. So obviously the next thing you probably would want to know how to do is how you do, for example, combinations. For example, in some languages you will use, for example, NCR 5, 2 for 5 choose 2. That would be the implementation, say in Desmos. N choose K would be another function in some other languages as well. Or you could just implement it yourself. For example, 5 choose 2 would just be equal to 5 factorial divided by 2 factorial times 5 minus 2, the quantity factorial. And you can just call the factorial function directly and you can calculate it manually. But there are predefined combination formula. There is a predefined combination formula in R, and this function is called choose. So if you want to do 5 choose 2 in R, you can just do choose 5 2, and that's going to give you 10, which is the exact answer. You could do, for example, 8 choose 5, and that will give you the correct answer. For example, if you choose 34 choose 31, you'll get some answer. And obviously, if the top index is smaller than the bottom index, then it obviously should be equal to 0 by logical definition. Right. So just as a quick example, if you are familiar with derangements, which is if you have 10 distinct objects, 10 different people, and you rearrange them, how many possible rearrangements of those objects are there if you don't want them to be standing in their original position, right? So some people will represent this as d to the power of n for the nth derangement. Right, so let's assume that we want to calculate the fifth derangement. So you take 5 people, rearrange those 5 people such that they're not standing where they used to be standing. That would be obviously the floor. So we're going to be rounding down 5 factorial, which is going to be equal to factorial 5, divided by e, which you can do as exp of 1. So that's the 2.718281828 constant, plus 0.5. And we have the answer of 44. So if you take 5 people and rearrange them such that they're not standing in their original position, you're going to have 44 distinct rearrangements of those objects with that structure requirement. Now that we have some of the mechanical basics implemented in R, now let us get into random sample simulations. So let's assume that we want to choose a random integer from 7 to 54. So notice that we're only focusing on one integer, so the question of with versus without replacement doesn't need to be considered here. So since we're choosing a random integer from 7 to 54, notice that we're allowing us to choose 7, we're allowing us to choose 54, and we're not allowed to choose, for example, decimals like 8.2, 52.6, or any decimals between the integers, implying that this random integer that we're selected is a discrete random variable. So, in order to choose one random integer from 7 to 54, you can use the function sample. So sample, and then the range for which you want to sample from, so 7 to 54. And then the size, this is how many numbers you are selecting. We're going to be choosing 1. And according to this implementation of R, it's chosen number 39. Now, let's assume that you want to sort of do a replicatable study where you can sort of do the simulation over and over again and get the same results each time, right? So for example, you want to sort of walk through this with your friends and you want to get the same random answers, right? So in some sense, pseudo-random. What you can do here is you can set what we call a seed. So set seed, and you can typically choose any natural number from say 1 to infinity, and that's going to be what you call your seed. So let's assume we choose the seed 45, and then we set that. So if we do this sample function, as long as you've ran this set seed 45 function, and then you ran the sample 7 to 54 size equals 1, most people, provided that R is in the same version and the same, code underlying background, everyone will get the same answer of 43. But notice that if I just run line 5 again, I do get a different number, and obviously if I run that line again, I do get a different number. But if I go back to my line 4 and I run that, and then I run that line 5 again, notice that it goes back to 43, which was the first answer that I got. And if I do it again, that gives me 17. And if I do it again, that gives me 52. So every time you want to sort of re-simulate a random process, you have to set that seed equal to the same number again. So that in some sense starts at the top of your pseudo-random list. So instead of choosing one random integer from 7 to 54, now let us choose several integers. In particular, let's choose 9 integers with replacement, right? Because if we do with replacement, we can choose the number 10 9 times, right? So let's, for example, use the same exact function sample. We're going to select, for example, from the same interval 7 to 54, and we're going to be choosing 9 values, and then replace is going to be set equal to true. So when I do this implementation, provided that I have an equal sign instead of a minus sign, that's going to give me a simple random sample of 9 integers chosen with replacement from the interval 7 to 54, including the boundaries. All right. So obviously, if I run that line again, that's going to give me a different sample. If I run that again, that's going to give me a different sample. And obviously, if I want to simulate the same exact samples, that's going to give me the same exact samples each time, just like before, provided that I didn't skip any entries in my list, of course. Right? So for example, let's clear that window, set the seed to be 45, for example. Notice that we have 43, 17, 52, 45, 35, 44. Set the seed again, and I should get the same two sets. So 43, 17, 52, 45, 35, 44, the same as before. Now, let's assume that we want to choose 9 integers without replacement. Then you would just do sample 7 to 54, size is equal to 9, and then replace is going to be set equal to false. So here, you are not allowed to get the same number more than once. Obviously, if you're choosing a small interval, for example 7 to 10, and we're choosing 9 elements without replacement, There are not 9 integers from 7 to 10. There's just 7, 8, 9, and 10. So the maximum size that you could do without replacement is going to be size 4. And obviously, if you try to run this code, you're going to have an integer or an error that says you can't take a sample larger than the population size when replacement is not set equal to true. So that's how you can do samples with and without replacement from a discrete numerical data set, in particular from integers. So let's do a little bit more of a realistic example. Let's assume that we want to select a random set of entries from a vector. So let's begin by creating a vector. So x is going to be the vector consisting of the names. Let's do Janet, Tommy, Mark, Susan, and Claire. So let's assume that's a set of your friends' names or something like that. And let's go ahead and set a seed. Let's set the seed to be equal to 32 because I want to sort of select the same elements from this set each time. So let's choose the first set. So we're going to be sampling from the vector x. We're going to choose 2 people and we're going to set replace equals to false. So this is without replacement. So you can't select Tommy 2 times. So that's going to be our first set. So notice that our first set contains Mark and Susan. And we can collect another sample of size 2 without replacement. And notice that our second set contains Janet and Claire, and we obviously can repeat this structure as many times as we want. But keep in mind, if I run S1 again, my set will change, and if I rerun S2, my sample will change because I'm not resetting my seed. So if you want to, again, resimulate that pseudo randomness, you need to rerun that seed and then set those samples, and that will go back to the original definition that we had before. So that's how you can do some simple random sample simulations. So another useful application, which we'll get into several examples of a little bit later, and let's assume we want to generate a Bernoulli sequence via a binomial distribution. Right? So for example, let's assume that we want to flip a coin, right? So we're going to flip a coin, and let's assume that 0 corresponds to heads and 1 corresponds to tails, and want to sort of simulate that process. So what we can do is we can create a new vector, say xb, and this is going to be the result of that simulation. So what we're going to do is we're going to do r binomial, and we're going to do 100 simulations. And what we're going to do now, and it should be binom, not binomial. So n is equal to 100, and then is going to come a parameter, which is going to be called size. So that's the upper bound for that string. So notice that we only have 0 and 1 as our outcome. Therefore, the upper bound for that sequence is going to be equal to 1. And obviously we need to set a probability value. If this is a fair coin, the probability of one of them is going to be 0.5 and the other 0.6 or 0.5 as well. But let's assume we want to sample with a probability of 0.4 for a success. So if we run that sequence, notice that we have a bunch of 1s and a bunch of 0s here. So in this simulation, if we define 0 to be heads and 1 to be equal to tails, then obviously we have tails, 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 heads, tails, heads, tails, tails, and so on. So that's sort of how you can simulate a sequence of events. But obviously we could have 0s for heads, 1 for tails, and 2 to be equal to, maybe it lands on its edge, I don't know. And let's assume that we want to obviously increase that number by 2 and run that. Then it's going to give you a bunch of sequences with a bunch of outputs with 1s, 0s, and 2s based upon the probability vector that you have sort of defined in this particular moment, which can either be a vector string or just a numerical for the first value, depending on the structure you want to sort of simulate that probability to be. The next thing I sort of want to go through is how to do probability mass functions in R if you have just an arbitrary discrete probability mass function defined on a closed and bounded interval. So let's assume that we have potential x values of -7, 1, 5, 9, 10, 12, 15, 19, and 23 with these associated probability values here. Obviously the length of x and its associated probability values should be the same length. In this particular example, notice that I have both lengths of 9. If it's sort of hard to see these two things here, you can obviously create a nice little table. Let's call it PMF. And let's do rbind, and we're going to do x and px on two different rows. And then we can run this particular function, and that's going to give us our x values on the first row and our probability values on the second row. And that sometimes is a little bit more easier to look at. Obviously, the sum of the probability values must be equal to 1, else it's not a probability mass function. And there should not be any negative values in our probability set. So if we do, for example, the sum of px less than 0, so this is obviously a logical statement, so px is less than 0 is going to return a bunch of zeros and ones. So if these numbers are less than 0, it's going to return 1. If it's not less than 0, it's going to return 0. So if all of them are non-negative, then we should have a bunch of zeros, and the sum of 0 plus 0 plus 0 all the way down to 0 should be equal to 0, and in this case it is. Therefore, since the sum is equal to 1 and we do not have any negative values, or we can also do, for example, the sum of all values bigger than 1, that should be equal to 0 as well. And therefore, since we have 1, 0, 0 for these three statements, therefore we have that px is a probability mass function for the random variable x, where x is defined on that particular domain. Now, let's get into some of the calculation things, such as expected value, second moment, and so on. So the expected value of x is going to be equal to the sum of xpx. So we can easily do that here by doing x times px. So what this is going to do is it's going to do element-wise products of these two vectors. So the first element of x times the first element of px, plus the second element of x times the second element of px, all the way down to the last element of x times the last element of px, and it's going to add up all of those products. And once we give that a run, we have 10.11 as our expected value of this particular random variable. So that's quite easy to do. Let's assume that we want to do the second moment of that random variable. So that's going to be obviously the sum of x squared times px. And that's going to do practically a similar thing, where x squared is doing element-wise squaring. So first element squared, second element squared, third element squared, and so on. That's going to be the vector x squared times that vector px, and that's obviously element-wise product, just like x times px. Sum all of those x squared px terms up, and you're going to have the second moment, which comes out to 158.95 for my particular example. The variance of x obviously is going to be equal to the second moment minus the mean squared. Now notice ex2 and ex are all numbers, therefore vx is going to be a scalar as well. Give that a run, and that's obviously going to be 56.74 approximately. And obviously the standard deviation is going to be equal to the square root of the variance of that random variable. So we have a standard deviation of approximately 7.53 for this discrete random variable that I have here. Now, sometimes instead of just looking at numbers, sometimes it's useful to look at a graph. So let's generate a frequency polygon for our discrete PMF. And we can easily do that by plotting x on the horizontal axis, px on the vertical axis. And let's connect all those. Let's give this a name first off. Let's call this PMF, frequency polygon. And let's connect all those points with lines. So you can do that type is equal to L. Let's connect all your points with a line, and this is going to create your probability mass function frequency polygon. So you see that practically most of this data is sort of hanging around somewhere about 10 to 11, and that should be obvious from our expected value being approximately equal to 10.11. Now, let's just do a couple examples on how to do probabilities if you have all of those things already predefined. So let's assume that we want to find the probability that x is equal to 10. This is actually quite easy to do if you don't want to search through your particular vector. So we can just pull from that particular probability vector and locate the location for which x is equal to 10. So the which function will return a set of indices that reference this particular vector x, looks for the location in x that has a value of 10, and that's going to tell you the location that you need to look in the value of px for that particular probability, because they should be matching up. So that's going to return the probability that x is equal to 10, which in this case is 0.18, which should match the associated table that we had before. So if we just call our PMF table, Notice that if we go to x is equal to 10, notice we have 0.18 there in a particular table, so this is definitely right. Let's assume that we want to do, for example, the probability that x is greater than 13. You could either do this manually, you could do, the probability of 15 plus 19 plus 23, add them all up, but in R, this is actually quite simple. We can do the sum of the px values for which have an associated index associated with all x values that are bigger than 13, and this is going to add up those associated values. So if you do 0.06 plus 0.11 plus 0.07, that's going to give you the probability that x is greater than 13 for this particular probability mass function. The last example that I want to do today is a particular probability mass function known as the hypergeometric distribution. Obviously, you can do this, for example, for Poisson, binomial, multinomial, and so on. But I think the hypergeometric distribution is quite nice and has quite a few interesting applications that you can solve with it directly. So obviously, if you know you're going to be using a hypergeometric distribution, you obviously should know a few parameters about it. In particular, you should know the upper bound for the number of possible successes, you should know the population size, and you should know the sample size that you're going to be collecting from this population. So let's assume that our population is of size, say, 35. Let's assume that the sample size we're going to select is going to be equal to 10. And let's assume that the maximum number of successes we can have in our sequence is equal to 7. So let's just quickly define k, n, and little n, and those are going to be our hypergeometric distribution parameters. Now remember, the probability that a random variable or hypergeometric random variable is equal to some value of x is going to be equal to c kx times c n minus k n minus x divided by c m n. That's the probability mass function for the hypergeometric distribution. So the first thing we obviously need to do is create our domain variable. Obviously, this is going to be a sequence. So it's a sequence. So from 0 to the minimum of two of these parameters. In particular, it's going to be equal to the minimum of the sample size and the number of possible successes. Because if the maximum number of successes you can have is 7, then you can't have 8 out of your 10 samples be a success. So it's going to be the minimum of the sample size. Let's actually make it a little bit more general, n and k. Right, so that's going to be creating a sequence. So obviously x is going to range from 0 to 7. And then we're going to have associated probability values, which we're going to be, again, calling to be px. So px is going to be equal to what? So we're going to be using the choose function here. So it's obviously going to be x, k, choose x. Notice k is a number, x is a vector, and then times choose. So it's going to be n minus k, and then n minus x. Again, capital N, little n, capital K are numbers, and x is a vector, so this is going to be a vector. And then this is going to be divided by choose n m, and that should return a vector with all the probabilities. So if we do h PMF, or the hypergeometric PMF, and we row bind the x values and the probability of x values, that is going to generate our probability mass function. So if we do, for example, plot x px, and then give this a nice little title, hypergeometric PMF, and then let's do a little line again. So type is equal to L. That's going to create a nice, well, it appears to be skewed right hypergeometric probability mass function. Right? So obviously we can ask a couple probability problems. For example, we can ask what is the probability that x is equal to 3? So that's obviously going to be the probability of x, and then we're going to be looking which x is equal to 3, and that's going to be giving me that associated probability value, which you should be able to see in this particular table, of course. So the probability when x is equal to 3, obviously we have 0.225741, which is the correct answer. And you could obviously do quite a bit more things. So for example, what is the probability that x is bigger than, for example, the mean of x? And if you don't know the mean of x, the mean of x is going to be equal to the sample size times k divided by capital N. And we can obviously do that. So we could do that via the probability, and obviously we're going to be doing the sum. So the sum of some probability values for which x is bigger than that particular value. So let's do n times k divided by m, and that's going to return to us that associated probability value. And if you're not sure if that's the case, well, what is mu x actually equal to? So that's going to be n times k divided by m. So in this case, mu x is equal to 2, right? So we want bigger than 2, so we're going to be adding 3, 4, 5, 6, 7, and 8. So we can obviously do that manually if you don't want to, type that out, but it will give you the same exact answer. So those are some of the fundamentals of doing discrete probability theory in the environment of the R programming language. In the next video, we'll look at some examples on how to do continuous probability theory basics in the R programming language as well. So I hope you enjoyed this video, and I'll see you in the next one. Take care.